To explain how Dr. Dow's mechanism works, imagine a spirograph. Now make sure that the inner gear has exactly half the teeth of the outer gear, and the only place you can trace is right on the edge where the teeth meet. When we run through the cycle, a straight line is created. Now imagine the whole thing is made of metal, and instead of a pencil, use a rod, of which the other end is attached to a pusher plate. When we actuate this mechanism with a pair of one-way valves, we get forward flow. This is simple harmonic motion. Other simplified crankshafts can achieve this as well. Now imagine the outer gear can rotate. It's automatically indexed with a spring so that when the piston comes up against a pressure head, the outer gear adjusts to meet the needs of the system. By adjusting the tension and position of this spring, the human heart's pulse pressure wave can be emulated. Other simplified crankshafts cannot do this. Finally, take the whole mechanism and squeeze it into a space that's smaller than 4 inches in diameter and half an inch deep.
The state of development of Dr. Dow's pump now is that he has a working prototype that demonstrates this unique and novel drive mechanism. The part that is novel, the part that is uniquely Dr. Dow, is right in here that turns this low RPM, high torque rotary engine into a very intelligent forward and backward motion. Exactly. And so, a conventional pump uses a mechanism, cams, to take that low RPM, high torque rotary motion and convert it to a back and forth motion of a diaphragm. But it is impervious to changes in the human body. It doesn't care. So if you bend down or cough or make some motion that drives your blood pressure up, the pump doesn't care. It just ejects against it, irrespective. And as such can generate super high pressures, 800 or 900 millimeters of mercury inside. And I think, although it probably doesn't acutely blow out the valves, it sets the stage for subsequent failure. Your pump, in contrast, during those moments when the pressure goes up, instead of ejecting the same way, it'll eject much more slowly over a longer percentage of that duty cycle. Sort of like the human heart. I mean, if you clamp your aorta, your heart doesn't die or explode. It kind of just does what it can for that one beat and says, we'll get them next time. Exactly. And that's sort of what your pump does.
Exactly. There are 3 main advantages to Dr. Dow's drive mechanism over current assist devices. When pressures increase, the stroke is intelligently adjusted. This intelligent adjustment happens during every stroke. In this way, the human heart's pulse pressure wave is constantly emulated.
What I think he brings to the table is a more savvy method of actuating those pusher plates that's more sensitive to what's going on in the body and may have a significant impact on how long the pumps last.
With the advantages described previously, the question remains, will Dr. Dow's mechanism improve the longevity of current ventricular assist devices?
First of all, we have to see if there's scientific merit, although on first evaluation it seems to, but it's very difficult to say, and that's just the nature of research. I can tell you that there are a number of projects that I or friends of mine have seen that seem to have a lot less scientific merit on first glance that ultimately developed into super valuable tools that are now being used in every hospital on the planet. Could this be one of those? Sure, of course it could. But right now we don't have enough information, and that's why you do research. Even if this drive mechanism, as Dr. Dow's envisioned it, doesn't pan out to be exactly what we think it could be, or to be used like we think it should be used, there's no question that the process of discovery, of doing the labs, of working with it, will reveal other things. Maybe other applications in fields other than heart failure, or other ways that it can be used in heart failure. If a project like this got funded, the Texas Heart Institute's an ideal place to do it. This is what we do day in and day out. And we have a whole cast of thousands down in the sub-basement where the Texas Heart Lab is, that are very eager for new projects of this type. Many of them are in the engineering program at University of Houston, where we have a collaborative agreement. In fact, I'm an adjunct professor in their bioengineering department. And we have postdocs and undergrads who are incredibly eager, incredibly enthusiastic, very bright people that eat, sleep, and dream this stuff. And this is the exact kind of project that they could really sink their teeth into. is Dr. Frazier. He's the Director of Surgical Research in Cardiopulmonary Transplantation and Development of the lab, and the guy with whom I work most closely. He's been one of the big moving forces in the development of this field. He helped design that AviaCor total artificial heart. He helped design the Jarvik left ventricular assist device. He's probably implanted more of these pumps than anybody in the world, and as such, you know, is a perfect guy to have involved in a project like this, and anything that I'm involved in, he's involved in as well. We could get a dedicated engineer to work with Dr. Dow to integrate his principles into a drive mechanism that would be able to actuate a conventional pusher plate pump with inlet and outlet valves, and then actuate that pump to exhaustion, that is, actuate it until it failed, and then we would have a benchmark to compare with the conventional pump. If indeed the sophisticated actuation mechanism that his very simple but elegant device is capable of delivering causes the membrane and the valves to last longer than the membrane and valves that are in the currently actuated pump, then we're on to something. If we can demonstrate in a convincing fashion to the scientific community that there's real value in a more sophisticated algorithm for actuating a pulsatile pump, then you won't have to ask for money. Everybody will want to invest in it because it's such a large unmet clinical need, and because the dollar amounts that the federal government is spending on these patients now is staggering.
Proving scientific merit is the next step for Dr. Dow's device, and research funding is required. Dr. Dow is seeking investors, venture capitalists, and philanthropists to share in his vision of making this dream a reality.
Like I said, there are huge numbers of patients in heart failure who have a very limited lifespan, and their last years are very, very difficult. And if a device like this provided value, you could have a significant impact on humanity. There's no question it's a novel drive system. I've never seen anything like it. It's really simple and elegant, and generally simple and elegant things have important roles. It's our job as scientists to find out what they are. And if it does pan out, the impact it could potentially have is staggering. This needs to be looked at, not only for the financial incentives, but also the altruistic ones. I mean, this is a large patient population that's being poorly served, and if this becomes a part of that solution, then to not investigate, it's criminal.
Dr. Cohn's views are his own, and he received no compensation for his part in this presentation.
If you'd like to give me a call or contact me through email, I'd be happy to answer any of your questions. I can tell you that Dr. Dow has sort of captured my imagination as the ultimate manifestation of an engineer, tinkerer, or doctor, and that in itself is probably worth investing in.